This video is an introduction to sets. A set is a collection of objects, and the objects in the set are called elements. Some examples of sets would be the set of all even integers, 2, 4, 6, 8, 0, -2, -4, etc. The set of differentiable functions is a set, and the set of keys on your keyboard on your computer is also a set. So lots of things can be sets. And the objects in a set don't need to be mathematical objects. One way to describe a set is by listing its elements between braces. So below are two sets. The first is the set containing the four elements 0, 1, 3, and 7. And the second is the set containing infinitely many elements. Dot, dot, dot is indicating that it continues. So -9, -6, -3, 0, 3, 6, 9, dot, dot, dot. This looks like to be the set of all integer multiples of 3. One comment here is that the notation is really important. So this notation here, we have braces that look like this, sort of squiggly things. And that is braces and not, parentheses or square brackets is very important. As we'll see later, it would denote different kinds of objects or lists or whatever. Okay. So as we see above, we have a finite set with 4 elements and also an infinite set with infinitely many elements. So a set with infinitely many elements is called an infinite set, and a set with finitely many elements is called a finite set. Two sets are said to be equal if they have the same elements in them. So the order of the elements in a set does not matter. So for example, the set 0, 1, 3, 7 is the same as the set 1, 7, 0, 3. The fact that the elements are rearranged in the set does not matter. They are still equal, whereas the set 4, 6, 8 is not the same as the set 4, 5, 8. So just having the same elements makes two sets equal. We often denote sets by uppercase letters. So we might say, let's let A be the set 0, 1, 3, 7, and let's let B be the set 4, 6, 8, the set containing the elements 4, 6, and 8. Then we want some shorthand to write things like 3 is an element of A, because we'll write things like that all the time in mathematics. So to write 3 is an element of A, we write 3 is an element of A. And so we could read that out loud as 3 is an element of A, as we have here, or 3 is in A, or just 3 in A. So that is the symbol for is an element of. Looks almost like a euro sign or something. 3 is an element of A. We can also list more than one element at a time using this symbol. So we could say 0, 1, 3 are all elements of A. We could write it like that. And if we want to say that some element is not in a set, then we just put a line through that is an element of symbol. So if we wanted to say 3 is not an element of B, we would write 3 is not an element of B. There are some sets that we refer to quite often, and they have special symbols associated with them. Some of those sets would be the set of all integers. So the set of integers contains positive and negative whole numbers as well as 0, -4, -3, -2, -1, 0, 1, 2, 3, 4, etc., etc. And that is denoted by a bold-faced Z. The set of natural numbers, so the counting numbers 1, 2, 3, 4, etc., is denoted by a capital letter N. Again, with this sort of extra line, these extra lines are originally meant to signify boldface, like in a typewriter, but we still have carried on this symbol. Similarly, the set of real numbers R contains all numbers on the number line. So the set R of real numbers is all the numbers from negative infinity to positive infinity, including, rational and irrational numbers like pi and square root of 2 and negative 3.672 and whatever else you can think of on the real number line, but not imaginary numbers, so not square root of negative 1. So the set of real numbers is everything on the number line. Okay, so those are three important sets, and those are symbols that you'll eventually want to just know off the top of your head. Z is for the integers, N is for the natural numbers, R is for the real numbers. All right, so sets can have elements other than numbers. So here are just some other examples of sets. We could say that A is the set of possible outcomes for two coin flips. So then in that case, A would be heads and then a head and then a tail and then a head, or two tails in a row. We could say that B is a set of vectors, and we could let B be the set of vectors 0, 1, 1, 0, 0, 0, 1, 1, for example. We can have sets that have sets as elements. So the set C here has the set 4, 6 as an element, has the number 2 as an element, and has the set 3, 7 as an element. And the elements of a set don't have to be alike. So we see that in set C we have the element 2 and then two elements that are sets. In the set D, we could say that, Bill is an element of D, the number 5 is an element of D, the set of all real numbers is an element of D, and Ted is also an element of D. So they can have sets as elements, and the elements of a set are not necessarily alike. A comment here is that the set 4, 6 is an element of the set C, but 4 by itself is not an element of the set C. So the set containing 4, 6 is an element of the set C above, but the individual parts of that set are not in C. Similarly, the set of all real numbers is an element of D, and 5 is an element of D because it is explicitly listed as an element of D. But if we pick some other real number, like 0 or pi, 0 and pi, while they are in the real numbers, they are not themselves elements of D. If X is a finite set, its cardinality is the number of elements that that set has, and the cardinality is denoted by vertical bars around the set. So unfortunately, it's the same as the notation for absolute value, but it should usually be pretty clear of whether you're looking at a set, in which case this denotes cardinality, or a number, in which case this would denote, the absolute value of that number. So here's just two examples. If A is the set of possible outcomes when we flip a coin twice, what is the cardinality of A? If C is the set we have above, what is the cardinality of C? So find the cardinality of both A and of C. And I would encourage you at this point to just pause for a second and make sure that you have a solution for this before going on. All right, so the set A has 4 distinct elements: heads, 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 tails, tails, heads, tails, tails. Those are the 4 distinct outcomes that can occur when you flip a coin 2 times. And so the cardinality of A is 4. C has 3 elements. So as we said, the set 4, 6 is an element, the number 2 is an element, and the set 3 containing 3 and 7 is an element. So the cardinality of C is 3. All right. Another special set is the empty set or the null set, and this can be denoted usually as sort of a 0 with a line through it. So sorry, computer scientists, in this class, don't write 0 like this. This is always the empty set. And we could also write it as braces with nothing in it. So those are 2 different ways to write the empty set. And note that the cardinality of the empty set is 0. There are no elements in this set, and so its cardinality is 0. A really important notational issue to point out is that the empty set and the set containing the empty set are different sets. So this is the empty set or the null set, whereas this is the set containing the empty set. And therefore they are different elements. One thing that makes them different is their cardinality. So the empty set or the null set, as we said, has cardinality 0, whereas the set containing the empty set, that is a set containing one element, and so it has cardinality 1.